to our fourth and final webinar series for the USACM Energy and Earth Systems Technical Thrust Area for the fall of 2025. So I just wanted to say a little bit about the technical thrust area and the webinar series. So my name is Irina Tazar. I'm the chair of the technical thrust area. We basically cover a variety of topics ranging from climate and earth system modeling to climate coupling to geomechanics to different kinds of energy, carbon sequestration, capture, storage, oil, gas recovery, and many others as well. We're a part of the U.S. Association for Computational Mechanics, and so if you're a part of USACM, you can join the technical thrust area for free. And if you're not, I would encourage you to join USACM to get discounts on conferences and workshops and things like that we organize. And so we do these webinars monthly. We're going to start again in January. I advertise to the listserv for the TTA, and I additionally advertise on LinkedIn. So if you follow us on LinkedIn, you'll get information about the webinar. So today it's my pleasure to introduce Dr. Nicole Aretz from UT Austin. She's the final speaker of the fall, and we're kind of focusing on early career and postdoc researchers in the fall. And she falls into that category. So Nicole is a postdoctoral fellow at the Odin Institute for Computational Engineering and Sciences at UT Austin. She received her PhD in mathematics in 2022 from RWTH Aachen University. In her work, Nicole combines a variety of uncertainty quantification methods for enabling predictive digital twins. Some of her interests include inverse problems, multifidelity approximation, optimal experimental design. To achieve speedups, she does a lot of physics-based reduced order modeling, in particular using the operator inference method developed at UT, originally at MIT, but by Karen Wilcox, who's at UT currently and who works with Nicole. And in recent years, Nicole has started working on ice sheet simulations as a target to demonstrate her digital twin work and her ROM work. And so that's what we'll be hearing about today. So I'll go ahead and hand it over to Nicole.
Yeah, thank you very much for the nice introduction, Irina, and thank you all for coming to hear me speak today. So this work has taken a while to complete, but now that it's done, I'm really proud of it. This was my first experience using ice sheet simulations, and it was a learning curve, but I think now that I've gotten to know the community a little bit better, it's just amazing of how friendly and welcoming everyone has been. So I'm very glad I've been selected to give a talk in the TTA. So just to give you an idea of what I have planned for you today, I'm going to first show you just how important uncertainty quantification is for ice sheet simulations. Even if we have just moderate climate forcing, there's a lot of uncertainty and we need to really nail it down in order to make decisions. Of course, ice sheet simulations are very expensive, especially if you want to do them to the detail and accuracy that you're used to. And for that, I'm going to introduce and show you 3 different techniques that are established in the mathematics literature, but maybe not as embraced yet at an applied level as one might hope for. So I'm going to show you the 3 different techniques and on a high level explain what their ideas are and how one might implement them. And then I compare all 3 techniques as on our model of the Greenland ice sheet. So I'm going to focus on Greenland today, not doing any other ice sheets, just Greenland. So that's going to be the main part of the talk, these 3 different topics. And then afterwards, because all of these multi-fidelity UQ techniques rely on surrogate models, I show you some of the surrogate models that we've been developing in our group, specifically for ice sheet simulations. However, just to stress, everything I tell you about before the multi-fidelity UQ techniques and our results for Greenland have only been using surrogate models that are just readily available within the ice sheet community. So different meshes, different physical approximations, because the idea of our work was really to be as beginner friendly and as low a level of threshold to do uncertainty quantification as possible. So I hope that with this talk I can bring that spirit to you as well. So let's start with why uncertainty quantification is important or is essential for ice sheet simulations. Let's think about just the process of what do we use ice sheet simulations for and how are they constructed? The end goal is to make policy decisions. So we want to inform our decision makers, such as our politicians, most likely. But we start off from all the sparse data that we have today. And it's important to understand that the data, even if it's satellite information, is sparse in comparison to just the sheer size of the ice sheet. So satellite information data is 2D, but the ice is 3D. And if we then think about like ice core measurements, that's pretty much point measurements in a 3D space. So data is really, really sparse, which means that no matter how well we understand the governing physics, the parameters that appear within the physical equations are going to be uncertain. And they need to be inferred because there's not a one-to-one correspondence of what we are measurements and the actual parameters. So think about ice core measurements, which are temperature measurements for inferring the geothermal heat flux, for example. There's an inverse problem in the middle, and inverse problems are notoriously ill-posed. So even though we do have quite a bit of data available nowadays, it's still sparse, and which means there's a lot of uncertainty in these model parameters. Now, this data, these inferred parameters, they get fed into the ice sheet model. We have the ice sheet model intercomparison projects to really compare the belief of different groups under agreed upon conditions, also following the economic pathways specified by the Intergovernmental Panel on Climate Change. So these different models set up by different groups make their projections of what might going to happen in the future following these different economic pathways, and all of that influences the policy decisions that we make down the road or make now to inform or to determine what is going to happen for our society in the future. But all of those are started with the data that we have, and the uncertainty that we are getting in these model parameters is going to propagate throughout this whole process. So it's very important we understand just how big this uncertainty is and how much it can perturb our projections of the future contribution to sea level rise or future change in the ice sheet. So for just to give you an idea of what kind of uncertainty I'm talking about, I took a look at the 6 ice sheet model intercomparison project, and specifically at the geothermal heat flux. So in the 6 ice sheet model intercomparison project, out of all of the groups that participated, 13 chose the geothermal heat flux that I've plotted here on the right, which was published by Shapiro and Ritzwaller in 2004, and 5 groups chose the one that I've plotted here on the left. So even though these are experts, they have chosen very, very different beliefs in the geothermal heat flux, which is basically the bottom boundary condition or a Neumann flux condition for the temperature model. So these are very, very different fields. Now the remaining groups in ISMIP 6 decided to go with different ones, but I've decided to contrast these two specifically because that's where the main opinions pooled on these two. So for us to model just what might actually be a ground truth, since the experts were pretty much split between these two, we modeled one random variable essentially as a slider between these two fields. So you can think of it just as the random variable that I wrote down here, where we sample from a uniform distribution and then have it be as a slider where we go 1 equals I'm being completely at the Shapiro-Ritzwaller flow, and 0 would mean I'm at the Graver flow, and any value between is just a linear combination of the two. So that's one uncertainty that is basically distinguishing the belief of what the experts think is realistic and present in our modeling scenarios. Another uncertainty that we looked at is the basal friction field, and that's maybe even more of an uncertainty because it just influences so much. So the basal friction field is used as a boundary condition, as a sliding boundary condition, for the velocity model of the ice. The ice is not stationary, but it moves, and the friction field at the bottom determines essentially how fast is it sliding out into the ocean where it melts, whereas maybe it is stationary. If there's a lot of friction, it basically means that the ice is frozen solid to the ground. And the way the basal friction field is inferred is that we're looking at surface velocity data that is taken by satellites and then solve a regularized inverse problem for the basal friction field. And here, there's just a huge variation in what you can achieve just by changing regularization parameters, for example, but also by changing different just data. So we looked at different data sets. So for example, we had a 20-year average of observed surface velocity data. We took that for our inference of the mean. But then starting 2015, we have data available for each individual year. So for our study, what we did was we inferred basal friction fields for all these different data sets. Right, so for the one averaged field and then also one basal friction field for the individual years. And then we fitted a log normal distribution for it. So that means we have essentially a normal, a Gaussian random variable with a informed covariance. Now, for our model, so we decided to go with these two uncertainties, the basal friction field and the geothermal heating. We try to, with our modeling setup, follow the ISMIP 6 experimental protocols as closely as possible. So for our modeling specifically, we use the ice sheet and sea level system model, ISSM, and we model temperature, velocity, pressure, and ice thickness. And so for setup, we used a bed machine for the geometry, did a historic run starting from steady state, and then got an initial condition eventually for 2015. So the initial condition for all the samples that I'm going to show you are the same, and then we're just looking at how much do these uncertainty change our output of interest, which is the ice mass lost by 2050, starting from the same initial condition. And then for our forcing, we decided to go with the socioeconomic pathway 1 2.6 scenario, which is a moderate climate forcing. And we made this decision because we want to show that uncertainty quantification is already very important when we're dealing with medium scale forcings, because the influence of the parameters and their uncertainty is just so large. So specifically to go a little bit more into the details, at each step of the evaluation, the model essentially iterates between, or our setup iterates between the thermal model, the stress balance, and the mass transport. So it solves for or updates the ice temperature at a time step, then updates the strain rate, ice velocity, and the temperature, and then the ice thickness, and then proceeds to the next step. So for our discretization, we chose a horizontal mesh that is relatively fine. So it goes down to a resolution of 100 meters and goes up to 15 kilometers. So from what I believe, this resolution is actually on par with what has been used in ISMIP 6. However, and I should point this out to the start or right from the beginning, for our vertical discretization, so for the three-dimensionality of the ice sheet, we only used 5 layers. So that is very coarse in comparison, and because of that, our degrees of freedom are actually still fairly low for the 3D variables. So we're at roughly 100,000 degrees of freedom for each 3D variable. Now, the reason we decided to go with a relatively coarse discretization was because we knew from the start and at the beginning of our study that we wanted to show comparisons with Monte Carlo sampling. And that meant that we had at some point make some decisions that would just mean, or that would just restrict how much our high fidelity model would cost. Because otherwise we would just be running simulations forever without actually getting much out of it. So we made certain decisions that just limited how much time a single model run would take. Another decision in this regard was that we are only modeling or are only projecting for the years 2015 to 2050 rather than going all the way to 2100, just because this time range, these 35 years, are already sufficient to show just how much influence these uncertainties can have. However, in time stepping, we are still following a CFL condition. So once the model runs, it decides by itself just how small or large the time stepping or time steps it can choose. And on average, what we call our high fidelity run is taking 65 CPU hours, and that is run in parallel. To go a little bit more into detail of which governing equations we're choosing, so for the temperature model, it's just the heat equation essentially. So this basically very much agreed on. Where I've written down here the basal boundary condition. So it's essentially the Neumann type boundary condition. The important one is the stress balance equation for the velocity and the pressure. So here we decided to go with a higher order approximation. So it's not the Stokes equations, but the first approximation thereof, so also known as the first order approximation, where we neglect some of the velocity in vertical direction so that we can start by solving for the velocity in x and y direction alone, and then later in recover the velocity in z direction and the pressure by enforcing some other conditions. And then finally, the mass transport model that is solved third. That one is an advection-dominated problem, so it's an advection equation. I believe ISSM adds some artificial diffusivity to it, but the important part is that essentially the ice thickness gets transported with the velocity field, and we have two forcing terms. So one of them is the surface mass balance, which we're using from the climate model with dynamic altitude adjustments. And then we have the basal melt, which ISSM internally updates using velocity, ice thickness, the ice temperature, the pressure to determine the pressure-dependent melting point, and also the geothermal heat flux. Now, the reason I'm going into this detail is just to show you where our uncertainties are coming in. So our uncertainty are the geothermal heat flux, which enters the thermal model, and the mass transport, and it's the basal friction field, which enters the velocity equations. So they are deeply integrated, even though they are not time dependent, they are deeply integrated into our governing equations. Now, following this model, let's take a look at just how much these uncertainties affect our projections. So here I've plotted for you on the x-axis the years 2015 to 2050, so our horizon for where we are taking the samples. And on the y-axis, we have the ice mass change compared to the initial condition. So the further the model goes, or the further the samples go down, the more ice mass change there is. Now for ice mass change, we are considering everything a change, even if it's just ice moving outside of our modeled domain. So not all ice that we are actually losing in our model domain is going to melt, but just to have a feeling of how much ice mass we are losing. On the right y-axis, I've plotted the equivalent in sea level rise, which sometimes is a little bit more intuitive. Now here we need to be careful though, because 0 is at the very top and then it's decreasing downward because it's inverse with the sign. So what we see here, so we have taken just a couple of random samples from our modeled uncertainties. So that's the 2 geothermal heat flux fields and then the basal friction fields that were inferred just from the different velocity data that the satellites gave for the different years. And we see there's this big spread, right? So for some samples, we get only about 5 millimeter contribution to future sea level rise, whereas for others, we're going all the way down to almost 25 millimeters by 2050. So that's a very big spread just from these couple of uncertainties. We can also see the dash dotted line is the projection that we are getting at the mean parametric uncertainty. And the dotted line is a Monte Carlo approximation that we did with 480 samples and is much more, so accounts for quite a bit of the uncertainty. And we see that using just a projection that is evaluated at the parametric mean is by no means informative about the mean of the distribution because it's a nonlinear model. So there's almost 5 millimeter sea level rise contribution difference between the actual or our high fidelity estimate of the actual mean and the projection at the parametric mean. Or we could go and take a step back and say, well, so all of this, what we call our high fidelity model, depends on the choices that we made for how we set up the model. And in particular, one of the biggest contributors that we have to our computational cost is the velocity model. So because the community knows that, there's actually a lot of physical work that has been invested into describing the governing equations. So by itself, even the higher order equations that we chose as our high fidelity approximation or high fidelity simulation are an approximation of the full Stokes model. So we could go and just decide, well, the higher order equations are too computationally expensive to really do UQ. Well, how about we just replace them with the shallow shelf approximation, where we go from the two 3D variables, we average the velocity in z direction, and instead we get two 2D variables. So that's a big decrease in degrees of freedom in what we are solving for. So let's compare that. So on the left, I have again the same projections that I showed you in the previously, and on the right, I've evaluated the same model except with the higher order equations replaced with the shallow shelf approximations for the same samples, and the color maps to the same samples. So so if you just choose your favorite red tone down here, find it in the right plot, and then you will see how it ends up. And what we see, very first of all, is that the shallow shelf approximation is by far not giving us the same spread that we observed previously, both in the less melt scenarios, where before we got all the way to 5 millimeter contribution, we're now at least 10, but also in the lots of melt scenarios. So there's a much smaller spread. But also, before I had all the colors arranged nicely in rainbows to show you that blue meant less melt and red meant a lot of melt. But now with the shallow shelf approximation, this ordering has gotten lost. So there are some parameters where the high fidelity model with a higher order equation thinks there's going to be a lot of ice mass loss, where the shallow shelf approximation thinks that, well, actually, I don't think it's one of the worst ones. So this comparison is to show you that if we want to if the left model is the one that we trust, and we trust the right model less, then if we want to do uncertainty quantification, we should not just replace the left model for the right model. We cannot go ahead and just say one model is too expensive. I trust it, but it's too expensive. I have to replace it. And the idea of multifidelity as uncertainty quantification is to say, well, if you trust the left model, then let's do UQ for it. But let's use the right model to help us do it in a statistically accurate way. And that's what I'm getting to next. So I'm going to show you 3 different types of multifidelity uncertainty quantification techniques that are mathematically well established and that all can be applied within ice sheet simulations. So the one that I want to highlight first and in the most detail is multifidelity Monte Carlo sampling. And I'll give you just a second. The idea of multifidelity Monte Carlo sampling is that we take a Monte Carlo estimate of our high fidelity model. So now here S0 is our high fidelity model, theta n are the different samples that we take, and then capital N0 are the number of high fidelity samples. So we take a Monte Carlo approximation of our high fidelity model, and these don't need to be many samples, just a couple of samples. And then we add approximations of surrogate models. So here the SM are surrogate model approximations of the same quantity of interest, so the ice mass loss. But here we are adding and subtracting a Monte Carlo approximation with a scaling factor. So we are adding here a Monte Carlo approximation of the high fidelity model, of a surrogate model with NM samples, and then subtracting a Monte Carlo approximation with fewer samples. And one important thing to note here is that the samples used in all of these different Monte Carlo approximations need to be shared. So I decide what is the highest number of samples I want to go to in total, and then draw samples for which I evaluate all models. So the idea being that if we have the scenario where one model thinks, oh, this should be a lot of melt, whereas another one thinks, oh, this is actually way less melt, that this information is captured. So that's why all the models need to be evaluated for the same number of samples as far as their individual sample sizes go. Now, one reason why we like using the multifidelity Monte Carlo estimator is because it's unbiased with respect to the high fidelity model. So if we apply the expectation operator to this estimator, and then use that the expectation is a linear operator, the expectation of the estimator is equal to the expectation of a high fidelity model plus 0. Right? Because these two Monte Carlo approximations that we did up here are going to cancel each other out statistically. So in the end, the expectation of the multifidelity estimator is going to be the same as if we had just done a Monte Carlo approximation of the high fidelity model alone. However, the mean squared error that we are achieving for the chosen sample sizes can be much lower than with normal Monte Carlo alone. So it's basically a scaling constant that enters here. And if we then do some mathematical analysis, we can find optimal weights and optimal sample sizes to bring the expected mean squared error of multifidelity Monte Carlo as low as possible. So I'm going into this much detail here just to show you that multi-fidelity UQ methods are not magic, but they just exploit correlations between high fidelity and low fidelity model in a statistically sound way. Now, another multi-fidelity UQ technique that you might have heard of is multi-level Monte Carlo, and I just want to highlight quickly what the differences are. So in multi-fidelity Monte Carlo, the one that I just showed you, we're adding and subtracting 2 times the same model, right? So we're adding an approximation of the expected surrogate model, and then subtracting the same one again, so that all of these cancel out in means. So that means that because we have the shared samples, we sample all models for some of the samples, and then all but the high fidelity model for some of the samples, and then essentially our sampling groups of which models share which samples become smaller and smaller. In multi-level Monte Carlo, it's a very similar idea, but just the structure of the estimator is slightly different, where we start with not a Monte Carlo approximation of the high fidelity mean, but actually a Monte Carlo approximation of the lowest fidelity mean. And then we say, okay, so we have a fine approximation of a low fidelity estimator. And then now let's iteratively update this original coarse approximation by looking at the difference between consecutive surrogate models, so that in the end, again, because things cancel out when we apply the expectation, where the expectation of the multi-level Monte Carlo estimator is also the high fidelity estimator. Now, the way multi-level Monte Carlo was introduced and the way the structure works out, it tends to be that the multi-level Monte Carlo approximator works particularly well when you work with mesh refinement. So that's particularly when you just fix your governing equations and then just play around with the meshes. So you can have finer resolution, coarser resolution, and then have these different differences be just how close the meshes are to each other. Whereas multi-fidelity Monte Carlo particularly likes when you get a lot of different physical information into the mix. So that's when you have the higher order equations, or you have the shallow shelf approximations. You might have all kinds of different other approximations, like the monolayer model or whatever you can think of. Now to go on, I just briefly want to highlight the different sampling groups. So a couple of years ago, a group came around and said, well, so here we are fixing the structure of our estimator beforehand. How about, and that's determined by these sampling groups, how about we optimize the structure at the same time as our sample sizes and weights? And that's what's called the multi-level best linear unbiased estimator. Now, this one is very complicated to explain, so I'm not going to try it. But the idea is that you're optimizing the structure of the estimator at the same time as the weights and the sample sizes. And by construction, both multi-fidelity Monte Carlo and multi-level Monte Carlo are possible choices of the multi-level best linear unbiased estimator. So the estimator that you get out of it is always going to be better than vanilla multi-level and multi-fidelity Monte Carlo. However, if we look a tiny bit closely at just how the multi-level best linear unbiased estimator is, how the optimization problem for it is solved, the thing is that the optimization problem can be very, very finicky and very sensitive to noise in your initial input data. So while it tends to be, when executed well, gives the best results and gives guaranteed the best results, it is much easier to go wrong with the multi-level with the best linear unbiased estimator than with multifidelity or multilevel Monte Carlo. So that's just my primary tool at the start with it. So just to summarize, basically we looked at these 3 different multifidelity estimators. They all have their advantages. They all have their reason to be, and let's apply them to the Greenland ice sheet. So same model as before. For our surrogate models, we use different meshes. So the top left here, so with the higher order equation and the fine mesh, that's our high fidelity model that I showed you before, where we constructed 2 other meshes that had coarser resolution. We also looked at the shallow shelf approximation as a type of surrogate. So this plot here at the bottom left I showed you before as well. And then also we applied the shallow shelf approximation to the medium and the coarse mesh as well. And then other surrogate models that we constructed was extrapolation type models where we simulated any of these models but for a shorter time period and then extrapolated where their projections might end up by 2050. So that's even coarser approximation, but at reduced cost. And then we also constructed an interpolation model that is just incredibly fast to evaluate, but also even less accurate than the others. So, and what I want to highlight here is that, first of all, how much the computational cost is changing from one fidelity to another, but also just how different these projections are once you look at them in some detail. And also here we had one outlier, but we're still including all kinds of outliers in the model just because there's no way we can catch all of them. And statistically, they're all gonna cancel out. So these are the surrogates that we worked with. And then we just decided to try out the different estimators. And specifically, we said, well, ice sheet models are expensive, so let's fix a computational budget and not go over it and see with each of these estimators what is the best we can do if our budget is not to exceed 5 high fidelity solves. Now here in the top left, I'm showing you the results for just standard Monte Carlo with 5 samples. And that's not gonna work, right? That's not gonna give you any reasonable approximation because 5 samples are just by far not enough to get results for Monte Carlo sampling. And by the way, the comparison here, the dashed line, is the uncertainty and the mean of a reference Monte Carlo approximation that was done with 480 different samples. So we see Monte Carlo we can't trust. However, with multifidelity Monte Carlo, that's the top right, or multi-level Monte Carlo, we essentially get for the mean approximation, we get a very good match to our reference approximation, and we have a reasonable uncertainty interval around them. So, and that's only while staying within the budget of 5 high fidelity solves. We also see multifidelity and multi-level Monte Carlo are performing very, very similar to each other. Now the best linear unbiased estimator here on the bottom right is even better. Okay, and it has to be by construction. So for this one, actually, one could almost say that maybe our reference approximation wasn't fine enough to really make a good comparison here because it's nailing it just so well. But again, here I should just stress with to use a little bit of caution because the multi-fidelity estimator, ML Blue estimator, is just a little bit finicky or very finicky to use. We can plot the same results just as uncertainty intervals. So here this the expected contribution to sea level rise by 2050. And here we have the Monte Carlo approximation based on the 480 samples, and then the uncertainty intervals for ML Blue and multi-level and multi-fidelity Monte Carlo. And we see, and as well Monte Carlo, and they all stayed within the allotted budget, and we see they all overlap, right? Which is what we want, considering that they are all unbiased estimators. Now for this one, we had decided to use a target budget. We can now also just ask the reverse question and say, well, I actually am interested in a target accuracy. So how much is it going, with these different estimators, how much computational resources is it going to cost me to achieve plus minus 1 millimeter accuracy for all of these different intervals? So that's the intervals we see here now. So here we had specifically, we decided on target accuracy of plus minus 1 millimeter in the uncertainty interval, and all of them achieve it, right? But they have vastly different costs. So going from Monte Carlo approximation, which we know is the most expensive, down to ML Blue, we almost have a factor of 100. I think it's factor 91. And multi-fidelity Monte Carlo and multi-level Monte Carlo are fairly similar by itself. Multi-fidelity doing a tiny bit better, but in the grand scheme of things, they worked very, very similar to each other. So this is just to show you that you can ask the reverse question and see how much can multi-fidelity UQ give us. I've plotted this information here on this graph for you, where basically on the x-axis we have the computational budget, so how many computational resources are we willing to spend, and then on the y-axis we have the associated root mean squared error, and on the left y-axis conveniently everything's plotted in terms of contribution to sea level rise. So this is the plus minus millimeter accuracy in the 95% confidence interval. And here we see that asymptotically, and I think that's very nice to stress, asymptotically the rate of all of these different estimators is the same. And that's what we expect because they all rely on Monte Carlo sampling. Really what all of these estimators are doing is shifting the constant in front of them. So that in the low budget regime, we converge much, much faster because the constant is just so much smaller. But in the end, the rate is going to stay the same. And that's why it's so important to get these initial estimates right from where we optimize the different samples and weights. Finally, just to end our study on multifidelity uncertainty quantification, I think it's important to take a look at, in these different approximations, just which models out of all the surrogate models that we made available to these estimators, which models did they choose? And as it turns out, the multifidelity and the multi-level estimator, they actually decided only to spend their available budget on four different models in total, three of them being the surrogate models and one of them being the high fidelity model. Here we've got just plotted on the x-axis the cumulative sample cost that has been allotted to the different models that they chose. So the multifidelity and the multi-level estimator, they basically just looked into the details of which models are there and which models best work for my structure, and then basically subsampled which models they wanted to use. The ML Blue estimator, in comparison, decided to go for 9 models and just really explore the whole variety of different surrogate models that are out there. Right, so we see there's different meshes, there's the different physical approximations, all the different types of models are in there. But that also shows us that it's just getting all of the information together, but then can also be very sensitive to the different models. Because for each one, there's just not that many samples to really counteract if there are any uncertainties in it. But of course, it is getting us a 91 times speed up compared to the 10 and 12 that we are seeing with multi-level and multi-fidelity Monte Carlo. So with that, I'm just gonna, because I know I'm running out of time, or have already run out of time, I want to show you a little bit of what we're doing in my group with surrogate modeling for operator inference. So for our multi-fidelity study, because we wanted it to be as accessible as possible, all the surrogate models that we used here relied on surrogates that are already readily available in the ice sheet literature, and in particular in ISSM. So that is physical approximations, like going from higher order equations to shallow shelf approximations, or that's numerical approximations by going from fine meshes to coarse meshes, right? But my background as a mathematician is in surrogate modeling and model order reduction. So there's actually a lot more that we can do in terms of building reduced order models that could then be used in a multi-fidelity setting like this. So one of the ideas in reduced order modeling is our projection-based model order reduction approaches, where we construct informed reduced spaces and then do a Galerkin projection onto the reduced space. And the advantage of that is that instead of working in a high-dimensional setting, like the finite element space, where you have lots of degrees of freedom, you can work instead in the reduced space, which is comparatively small. But of course, it does mean that you're making an approximation error by going from high fidelity and finite element resolution to whichever space you chose. However, it can still work. And we specifically followed we used the operator inference approach, which is a learning technique for constructing this, or for learning the Galerkin projection. I'm not going to go into any detail about it, but we used it on our model of the Greenland ice sheet. So specifically, we did do some approximations where we, just for demonstrating that the operator inference technique could work, where we approximated the velocity field as constant in time, and then just constructed a reduced order approximation of the ice thickness. That was the idea, and we also only looked at one parameter for the basal friction field. So that was for demonstration, but we see that here in effect, for most of our training parameters, the error actually stayed very, very low, and on average, we got an error below 5% even for other parameters. Though I should mention that the high error here towards 2020 is because the reduced space that we constructed was for absolute error. So we constructed reduced space so that the absolute error would be below a certain threshold, but I'm plotting the relative error, and the relative error at 2000, or our initial condition here was 0, because we're looking at the change to the 2020 ice mass loss. So really, the important thing to look at is the effectivity, which is the ratio of achieved to best possible error. And there we see that actually our reduced model does very, very well compared to the space that it has available. Another mathematical test that we did for building surrogate models was a combination of operator inference and SFOM learning. Here we looked at a model of the Pine Island Glacier and basically split it into two domains, one where we have a projection-based approach, one where we have a high-fidelity approach, and then learned different techniques. And the important thing here to stress is we looked for one at how well the reduced order approach on the right is approximating the float, or the boundary between floated ice and grounding ice, and it actually performed surprisingly well. So we were very happy with these results. So these are under no melt conditions. This under high melt conditions. Again, on the right is our surrogate model projection, and on the left is the ISM projection. And it's just doing very, very well with that. So with that, just to give you a brief summary, really we built out a model of the Greenland ice sheet following as closely as I possibly could the SMIP6 protocols, with some step backs just in computational cost to make comparison with Monte Carlo possible, and then applied 3 different multifidelity approaches: multilevel Monte Carlo, multifidelity Monte Carlo, and the best linear unbiased estimator to them, to show that they all have merit to be used in UQ for ice sheets. So in the future, I hope to find collaborators to apply all of these techniques or one of them to Antarctica and to invest some work into ML Blue because it has just so much potential, but currently still has some finicky drawbacks. So with that, thank you very much for your attention and welcome any questions.
Thanks, Nicole. That was great. Um, are there any questions online? So you answered most of the questions that I had throughout the talk, but I was curious. Maybe I missed it, but it was a little bit fast at the end about the
Yeah.
reduced order
Mhm.
modeling work. So was this an operator inference type of an approach that you applied
Yes.
in the end? Then,
Yeah.
and so and was it because the operator inference is based on a polynomial approximation, right? So were you using like a quadratic ROM or
Yeah. So I skipped very much through this
okay, so I didn't miss it.
last section because I already knew I was out of time and I didn't want to stress people's patience with me too much. So we did use an operator inference approach where essentially just for the people who are not familiar with it, the goal is that we would very much like to build a projection-based reduced order model, but where the high fidelity model, for example, ISSM, is just not set up for us to freely compute all of the operators that we would need. And then operator inference solves least squares learning problem to get the Galerkin projection from the available snapshot data. And then, so this work was, or we used this example as part of an operator inference paper, so not in the ice sheet community, but we used the Greenland code to demonstrate the mathematical approach in a math paper. And that's why we made here some quite a few simplifying assumptions just because it's a math paper. Um, so for one, when we were building our reduced order model approximation, we just decided that we were not gonna um, uh, try to recover the whole ice velocity for all of the time steps, but instead, because we know the velocity changes very slowly, just have it be constant in time, and just approximate the influence of the basal friction field. And then we spent the main part of the work on approximating the ice thickness equations, which are essentially advection diffusion equations. And because of that, we actually get away with a linear model as long as in a quadratic way we include the ice velocity. And then a big part of it, though, was to learn approximations of the surface mass balance and of the influence of the basal melt, because that one changes on a yearly basis and also has these altitude-dependent adjustments. So, and in combination with, like, we chose a 30-dimensional space, this was actually still a very, very big learning problem, and in particular had all of these physical approximations in there and structural approximations, which made it very difficult for operator inference to use. However, it did work out with the technique that we called nested operator inference, which we've submitted in the summer. So I'm pointing you all to the references if you have any further questions on them.
Yeah, no, that makes sense. Yeah, and that's clever that you're because I mean the issue is if the full order model has generic nonlinearities like full Stokes, there's going to be a limit on how well like a quadratic operator inference will do. But at the
Yeah.
same time, I think the idea of the domain decomposition based coupling is a really nice one because I mean, you would, the idea of sort of using the reduced order model only in regions where there isn't as much happening and relying on the full order model where there's more happening. I think that's a really promising approach to sort of
Yeah.
mitigate this partially to just have like the quadratic model in certain regions, not everywhere. Um,
Yeah, exactly. So that's essentially what we did in
Yeah.
Leonidas's work, was where we split the domain into one part that was for operator inference and one part that was for sparse full order model learning, and then had them talk to each other, and that worked very, very nicely.
Yeah. And I'll just also comment, I don't think that the 5 layers is that big of a deal, that assumption.
Okay.
A lot of modelers or glaciologists, they actually just use that. And a long time ago, I actually studied this, like the impact of that. There is some impact on the vertical resolution, but it's not really a huge one. So I don't think you're losing a whole lot by just doing the 5 layers there.
Oh, that's great. Thank you.
Yeah. Other questions? Okay, well, I won't dominate the Q&A here. I'll let folks go.